So this is the data table that you guys should have filled in. Okay, just a reminder that this here, y'all, the gas that's being collected is butane, and the gas in here is equal to atmospheric pressure. So that's atmospheric pressure, and it's equal to the gas that's being collected, butane, and the pressure of water vapor. Okay, we have to look up this value here, but we're going to be solving for this value, and this value was the one that was on the iPad. Okay, so these are the values you guys should have copied down while watching the video. But if you guys didn't copy it down, please copy it down now. We're going to take a look at atmospheric pressure. Okay, atmospheric pressure is given to us in hectopascal, but I need it to be in kilopascal because our water vapor pressure is given to us in kilopascal. So in order to do that, all I have to do is move my decimal place one place over to the left. That turns it into a kilopascal. So I have 102.24 kilopascal. So this right here, y'all, is my atmospheric pressure. So I'm going to cross this out and rewrite it as my kilopascal value. The reason why we needed the water temperature is to look up at what temperature that water vapor pressure is at. So at 24 degrees, y'all, water vapor pressure is at 2.99 kilopascal. So this is the pressure of my water vapor. I got this value from a reference table. Okay? So now I can solve for the pressure of butane. That's what I want to use in order to calculate the number of moles of butane. So again, I want to remind y'all that our goal is to calculate the molar mass of butane. Okay? So let's do it. We have atmospheric pressure equals the pressure of butane plus the pressure of my water vapor. So I'm going to get the pressure of butane by itself. That's the variable I'm looking for. So I subtract both sides by the water vapor pressure. And when I do, I rearrange my formula to get this here. So now I substitute. So pressure of butane equals my atmospheric pressure, which is 102.24 kilopascal, and then my pressure of the water vapor is 2.99 kilopascal, and then I get 99.25 kilopascal as my pressure of butane. That's the value I need in order to use the ideal gas law. But guess what? I want it in atmospheres. So I'm going to convert this to atmospheres now so I can use my R constant that we have in class. So kilopascal, we know that 1 atmosphere is equal to 101.32 kilopascal. Kilopascal cancels out, and then I divide my value. Keeping my 4 sig fig, I get 0.9796 atmospheres. So that is the pressure of butane. Okay, so I'm going to use that value to plug into my ideal gas law. So these are the three questions that we must answer in order to determine the molar mass of butane. Okay? Well, just a reminder from the previous slide that the molar mass is calculated as grams divided by moles. So I'm going to use the ideal gas law to determine the number of moles, and for the grams, I'm going to use the experimental data that I got. Okay, so there we have it. So the mass of butane collected Joule, that's the mass that we measured, the initial mass of the lighter and the final mass of the lighter. So that, I'm going to take the difference between the two. So we had the initial mass minus the final mass in order to get a positive number because we were decreasing it. So our initial mass was 21 grams minus 20 grams, and that got me 1 gram of the butane. Okay, in order to determine the number of moles of butane collected, I need to use the ideal gas law. Reminder, ideal gas law is PV N R T. Okay, so I'm going to use the guess method. So the givens on the side, I always write it in the order of the equation. So my pressure was calculated to be 0.9796 atmospheres. My volume collected, 93 milliliters. We don't know moles. Our universal gas constant, 0.0821. And the unit for that would be ATM, liters over moles Kelvin. And then our temperature, y'all. Temperature of the water was 24 degrees Celsius. Add 273 to that, and we get 270 or 297 Kelvin. So I need to convert any units that doesn't match the universal gas constant unit. So I have atmospheres. I need liters. So I'm going to convert this to liters by moving the decimal place 3 places over to the left to get 0.093. And looks like everything else is good. So now, box my unknown that I'm looking for. Equation time, PV equals nRT. I'm looking for N. To isolate N, I divide both sides by RT. These guys cancel out. I'm rearranging. So we have our equation. Next step, substitute. So N equals P is 0.9796 atmospheres times volume would be 0.093 liters divided by the gas constant with its unit, atmospheres, liters over moles Kelvin, times that temperature, 297 Kelvin. And when I do, I get, with 2 sig figs, 0.0037 moles. To calculate the molar mass of butane, reminding y'all that the equation is grams divided by moles. So I had grams, 1 gram, and then the moles I just calculated. And when I do, I get 270.27 grams per mole. So the actual molar mass of butane is much smaller. It is 58.1 0.12 grams per mole. So I'm going to chalk this number up to imprecise equipment at home. My scale doesn't go out to any decimal place. It was a kitchen scale to the nearest whole number. So this 1 gram definitely is not precise at all. So I'm going to chalk that up to what's giving me such a high value, y'all. Again, record or write down any thoughts on why the values differ based on the video that I created. Okay.